Hello and welcome to the course on machine learning for networks. In this course, we will cover the basics of machine learning with a particular focus on applications on communication network problems. This is an introductory course, so even if you've never heard about machine learning before, you will be able to follow. On the other hand, even if you know already some machine learning, I'm sure you will still learn new things here. Fortunately or unfortunately, machine learning is so vast and evolving so fast that there's always a new thing to learn about. You don't need a lot of pre-requirements. You just need to know what is a matrix, how to multiply matrices, and what is a derivative, and that's all. I'll try to give the same importance to theory and practice. So in every lesson, I'll first describe the concepts behind the various methods, and then I will immediately walk through the Python code to understand how to apply them to real communication network problems. All the code is in Python, so it is required you already know this programming language. And I will explain you in this lesson where to get the code and how to run it yourself. I hope that by the end of this course, you will be able to first understand the common concepts in machine learning so that you will be able to explore new methods, new algorithms yourself. This is particularly important because of the continuous evolution of this field. And second, you will be able to carry on a data science project, which can be useful in your career. Not only in communication networks, even if this is our main field, but in also other kind of problems. So let's start to talk about the actual content of the course. So I will start to give some definition of artificial intelligence and machine learning. Then we will discuss some applications to communication networks, and we will define supervised, unsupervised, and semi-supervised learning. We will already start to write some Python code to perform data exploration. So what is artificial intelligence? Well, there is no unique definition because it is sort of young field. For sure, there is a lot of misconception and sort of sacrality around artificial intelligence that we will try to destroy in this course. So let's take some sentences from a consulting group website. So they say that AI, artificial intelligence, allows machines to sense, comprehend, and act and learn. AI promises a new era of disruption and productivity where human ingenuity is enhanced by speed and precision. So you see that a data scientist is sort of seen as a magician who is able to use this crystal sphere of artificial intelligence to solve any problem. Of course, this is the vision that many people have, and so we risk to demand too much to artificial intelligence. So in this course, we will try to escape from this vision. We will have an engineering vision instead, more practical one. So we will look into this crystal sphere to understand what are the single gears that determine the inner workings of the various algorithms. So we will see that at the end of the day, artificial intelligence is not at all a crystal sphere, but it's just a smart combination of tools, mathematical tools that already existed before, but that now they are combined in a nice and intelligent way. These tools are statistics and optimization at the end of the day. So combining in a smart way these two tools together with the huge amount of computation capabilities that we have that allow us to perform huge calculus in milliseconds. These two factors led us to the rise of artificial intelligence in recent years. So we have to have clear in our mind that there is no, even if we talk about artificial intelligence, there is no real mysterious intelligence in machines, and machines will never be able to understand. These are just simplifications. The reality is that machines are still stupid as they were before. All that they can do is just to minimize or maximize functions. That's all. So why this is important to do so? Because experience has shown that blindly trusting machine intelligence can can lead us to many kind of dangers. First of all, financial loss by countries or companies if they make the right choice that is suggested by an algorithm. Social inequity. It happens when you try to control population or to decide laws based on the guidance that algorithms give you. And deaths, typically in experiments where artificial intelligence has been deployed to drive autonomous vehicles. So the only way to prevent these dangers is to really understand artificial intelligence in a practical way, to see what's inside this ball and to use it properly. So in the big family of artificial intelligence that we will define in a more precise way in one slide, we find inside this family another family that is machine learning algorithms. And inside machine learning, the so-called deep learning, where you use neural networks to perform the machine learning tasks. So in this course, we will focus on machine learning. So we will see many methods. Among them, we will also see deep learning and neural networks. But we will also explore many other methods. So for sure, deep learning is the trendiest family of methods. But it's not the only one, and there are other algorithms that sometimes are easier to use and even more efficient. The term artificial intelligence was very likely coined in the so-called Dartmouth workshop, where many very important scientists of that time, like Claude Shannon and Marvin Minsky, united to try to think about ways to let machines reason as humans. Okay, so let's try to define what an AI algorithm is. It is an algorithm that is able to take complex decisions or give complex answers in order to maximize or minimize a utility function. For example, suppose your utility function you want to maximize is the financial gain of your investments. Okay, so you have to take complex decisions that are this F, whether should I sell some stocks, should I buy them, etc. These decisions are complex because they are based on many factors determined by the environment, that is everything that surrounds you. In the case of financial investment, this environment is the set of laws of the countries around the world, in the investment of the other companies, etc. Okay, these are many factors that you should take into account, and these are represented by the E in this formula. And at the end of the day, you want to maximize your utility, the amount of money you gain. That is represented by this U. And given that the environment is stochastic, so there is a lot of randomness relating the utility to the state of the system, it makes no sense to maximize the utility. You can only maximize the expected value that is represented by this V. Okay, so an AI algorithm is supposed to solve this difficult maximization problem. Machine learning algorithms is a subfamily of AI algorithms that improve their performance by repeating the task. So, for instance, an algorithm that tries to make investment decisions many times and observes the outcome of its decision and tries again and is able to improve this decision based on its observation, this is a machine learning algorithm. So in other words, machine learning is a set of methods that take advantage of big amount of data, which correspond to the different experiences, to maximize or minimize the utility function. So the goal of this course, to be more precise, is to understand machine learning, first theoretically, and then also to put it in practice. So to do so, you first need to be able to use Python libraries that are already available, like scikit-learn or Keras or TensorFlow. So it is very important you don't try to write yourself implementations that already exist, because first of all, you will just waste your time, and also you will be more likely to make some mistakes. While if you make the effort to understand libraries already developed, you will be sure if there were an error, some other people would have already found it. So we will put our accent to use pre-existing libraries. Then you will be able to combine all these existing pieces to carry on a data science project where you have a high-level task, and it's up to you to choose the right piece of code and the right methods to obtain the results you're interested in. Then to carry on a data science project, it's a lot of trials and errors. So here it's up to you, to your fantasy, to your experience, to try to different configurations of the algorithms, different combinations of the various methods, etc. So there is no fixed guidance in this. It's up to you to try many things. Where you have to be careful is in the interpretation of the results. So here we will pay a lot of attention to have a robust interpretation of the result. So because otherwise you risk to have the results and to give the wrong interpretation based on this. And finally, you will be able to apply machine learning to practical network problems in particular, but the skills you will develop will be useful in any data science problem. So why machine learning is particularly relevant in communication networks? First, because we can say networks need machine learning, because nowadays networks, if you think about the internet, is extremely complex. There are a lot of users, human users. Nowadays, machines are becoming also other important actors of the internet. They communicate each other on the network. And there are many protocols, many applications that coexist in the same network. Moreover, 5G calls for flexible networks that are able to observe the current state in terms of available capacity, load coming from users, etc., and adapt the utilization of these resources to these conditions. And since these conditions can change very fast, this readaptation must happen within milliseconds. So we need decision algorithms that are very fast. Moreover, the traffic in our networks is nowadays encrypted. So it is a sort of black box. We cannot look inside it. So we need to be able to take decisions just by observing the outcome of this black box. Therefore, the classic methods of modeling your network and then control it based on this model cannot simply work anymore. We need data-driven methods that just learn by experience, by controlling the network, observing the results of these control actions, and improve these control actions with the time. This is why machine learning is a promising avenue for the networks of the future. Moreover, networks offer a lot of information because all the equipments are able to collect in a very fine-grained time many measurement information. So we have a lot of possibility to improve our machine network algorithms. So you will be asked to perform, to carry on a data science project using machine learning on different tasks in communication networks. You will be asked, for example, to predict what are the application protocols that are running in a certain network just by looking at information at the level of IP and TCP. You will be asked to infer the quality of experience perceived by users when consuming multimedia content just by looking at network information, and to discover if there is an attack that is going on in your network. You will also be asked to do predictive maintenance, meaning to understand if in a production plant, for example, there is some defects that can propagate in your plant, to get it as soon as possible and to remove the problematic object from your plant. We will also talk about discover frauds in credit card transactions, apply machine learning to high-speed virtual network functions, etc.
So in terms of material, the best source is Google. So whenever you have a doubt, etc., just Google it and you will likely find the answer. Then I suggest you to use two books from Jérôme, the first one, and James, the second. And the first one can be found in the Mediathèque of Télécom Sud Paris and is available online for free for you. And the other one is also available online, and I put the links there. Then another source I invite you to use is my website. So if you go in Google and you look for my name, you will go to my website, and in the course page you will find all the slides, as well as the GitHub page where I put all the code that you can immediately run yourself. Okay. Then to run your code, you don't need to install anything in your machine, any library, nothing. You just need a browser, Firefox, Chrome, whatever you want, and a Google account. In fact, we will be using Google Colab, which is a platform, a cloud platform from Google that is available for free and allows you to run Python code directly there using their GPUs and TPUs. So let's start to talk about the actual machine learning methods we will see. We have mainly 5 families of machine learning methods: supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning, and recommender systems. In supervised learning, you have a dataset composed by different samples, or also called instances, and these instances are described by a set of features, which are their characteristics. For instance, if you have a dataset of internet connections, each sample is a connection, and the features could be number of IP packets exchanged, inter-arrival time between packets, number of retransmissions, etc. And then you also have a label, which can be either a category or a number. So, for instance, if you want to understand if an internet connection is being used for web browsing, or for video streaming, or for file download, the category is what you want to find. Okay, so in this case, when the label is a category, we talk about classification. If instead the label is a number, we talk about regression. To give an example, with the same dataset, you may want to find by just looking at the internet connection features, you may want to find the quality of experience of a user that is watching a video. And this quality of experience may be expressed by a number from 0 to 5 stars. So in this case, the label is a number, is this 0 from 5 stars. And in this case, supervised learning is called regression. Then we have unsupervised learning, where you don't have a label. You just look at the features of your datasets, and you want to get insights from your data. You have 3 categories of unsupervised learning. Clustering, where you want to find similarities between your samples in order to group them together. For instance, if you're a web site administrator, you may want to group the users of your website in similar groups, so that you can provide better targeted advertisements, for instance. Then you have anomaly detection, where you try to find the outliers in your dataset, meaning the samples that are far from the other samples. Their features are completely different from from most of your datasets. So these anomalies may be due to malicious users trying to attack your system, or problems in your infrastructure, in your system. If we come back to the same example as before, internet connections, you may find internet connections with a lot of packet retransmissions. These may be due to a kind of attack, or simply a link that is malfunctioning. The third category of unsupervised learning is dimensionality reduction, where you have a dataset with a lot of features and you try to compress the information using less features. This is very useful because when you want to process with other algorithms your dataset, the less features you have, the more efficient is your processing. Semi-supervised learning is in the middle between the previous two. So you have a data set full of unlabeled data and just few labeled samples. An example is you are a website providing streaming music, and your samples are your songs. And you don't have a category for your song, just few of them, but you can group together songs that are similar in terms of their spectrum, their timing, etc. And then it suffices you have few labels in each group that you can categorize the entire group. Reinforcement learning is a method that we will not see in this course, and it deals with constructing an algorithm that is able to control a system by just interacting with the system, changing its status, etc., observing the consequences of this interaction, and improving the way of interacting the system over and over again. But we will not see it. And then recommender systems, in which you have users on one side and items on the other side. These items could be movies, songs, products, if you're an e-commerce website. So you know already some preferences of users toward items. And then whenever a new user comes, or you want to understand what are the items that he would prefer the most. And to do so, you use the similarity of this user with respect to the other users, and you propose items that are appreciated by these similar users. So these are the methods you will learn in this course. So for supervised learning, you will learn how to do regression and classification, clustering, dimensionality reduction and anomaly detection for unsupervised learning, and recommender system if you will have time. And to perform these tasks, you have different tools. And as you can see on the right, neural networks is, we can say, the most powerful tool, because you can use them to perform any task. But neural networks is not the only tool, so we will also explore the others. Along the entire course, there will be few concepts that are of central importance and that I will repeat, you will encounter over and over again. The first one is to treat properly your data, so to use the correct protocol. And whenever you're given a data set, the first thing you should do is to divide it into parts, the training set and the test sets, and work to improve on your model entirely on the training set. You have to really forget about the test set. Only after you have the final model, you selected one of the possible models you tried, then you can check its performance on the test set. This will give you an idea of the performance of the machine learning model you constructed in real situations with samples that it has never seen. Another important concept is the parsimony. So you will see that every algorithm has many parameters, so more or less parameters, let's say. So the more parameters you allow to your algorithm, the more flexible it is, so the better it can adapt to your data. But if it adapts too much, this is a problem, because it will not be able to generalize. It will just be able to perform well on your data, but not on new data that you may encounter later. This problem is known as overfit. So in order to avoid it, you have to be parsimonious. You have to limit the parameters to the ones that are really needed. And then randomness. Many machine learning algorithms have different random decisions in their inner workings. So if you repeat the same algorithm on the same data several times, you may have different results. This is a good thing, because randomness allows algorithms to be a bit imprecise. So they cannot adapt too well to the data sets due to this imprecision. And so this allows to avoid overfitting. We will see how we encounter this randomness in different algorithms. This is the notation I will follow throughout this course. So scalars are just small letters. Vectors are small bold letters. Vector transpose is indicated by this T, and then matrices are bold capital letters, and sets are calligraphic letters. Any data science project is composed at least by 4 steps: pre-processing, data exploration, model selection, and performance evaluation. Pre-processing means that you will download the datasets. You may need to parse files or to put different files together. In data exploration, you start to visualize your data. You check what are the features that you have, what is the data type of the different features and of the label, what is the probability distribution of your features, etc. In model selection is the core part of a data science project, in which you try to construct different models, supervised or unsupervised. Then you select one of them, and you go to the 4th step, that is performance evaluation. So you judge the quality of your model by measuring the accuracy or other metrics depending on the model you're using. So data preprocessing changes completely from a dataset to another, so there's not much to say. It's up to you to understand what is the treatment that your data needs. So today we will immediately dive into data exploration, and we will see these concepts, mean, variance, standard deviation, percentiles, etc. We will see them directly into the code. Then I would ask you as an exercise to, after we go through the code, to write the definition of these quantities that we will see in this slide, and pay attention, because these formulas and these definitions may be asked during the exam. So let's go to the code. Okay, so as I've told you, to get the code, you just go to my homepage and you go to GitHub page. Here you have different code for each different class, and we will start with 1, of course. So the code is in this format: IPython notebook. You will see that there are also other scripts that whose name starts with ignore. You can ignore these scripts, of course. These are just Python code that I needed to write in order to do some pre-processing, but there's no conceptual content there. So you can go directly to exploration. Okay, so you can see already that in the Python notebook you find my comments, some figures, and also the code. You can already see the code and the result. So even if you don't run it, you can already see everything, okay, the content. But it may be interesting to run and to modify some piece of code if you want. So to do so, you just need to click on this button that I added, opening Colab. This is the same notebook, Python notebook, but opened with inside Google Colab. Okay, actually, when you are in Google Colab, you are in a virtual machine dedicated to you, and if you want to see the files that are in your virtual machines, you just click on this symbol, and you can find the files. Okay. Here you can see the utilization of your resources, the RAM and the disk. Of course, Google gives you a limited amount of resources. You can't consume them all, and you can monitor them with this. What else? A Python notebook is composed by different cells. You have 2 kinds of cells. This one, for example, is a text cell in which you can write text and you can add pictures. Or this is a code cell where you can write Python code. Okay. Another thing that is important to check is you click on runtime, and you make sure you're using Python 3. Also, when we run neural networks, we will select hardware accelerator, GPU or TPU, but for the moment is not very important. If you want to modify any cell, you just double click. For example, here I'm removing the word hello and I'm adding hi. Let's see. So now I see hi. Okay, and you can also remove the code. You can also modify the code. This is a comment. Okay, to run a cell, you just press Shift Enter, and you run a cell. you can also write Linux command line commands. For example, here, if you use exclamation mark before at the beginning of a code cell, you can use standard Linux commands. For example, ls is showing me what are the files that I have in my machine. What else? I can show what is actually I can show just the first lines of df.a of this file here. Okay, so it's actually nothing more than a Linux command line. Among the commands, the one that you will use the most is wget to download external datasets like this. So here I'm downloading the dataset, and actually the result is df.a1.csv, so .3. So you see that now the downloaded file is in our folder. Okay, so you can also remove the files here. Oops, you can remove it, delete file, etc. So this is quite simple. In this notebook, we will explore a dataset called request. I added the link here. So this is a work from people from Columbia University, and it appeared in a conference called ACM MMCs in 2019. So what they do, their goal is to infer video quality just by looking at network information, so number of packets exchanged, etc., number of bytes downloaded, etc. So why it is important? Because if you're a network operator, you would like to infer if your users are experiencing good quality when downloading multimedia file or not. But you can't look into the traffic of the users because it is encrypted. So you need methods to infer the quality of experience of users just by looking at network information. And this is what they do. So actually they created a testbed where you have a client that downloads a video from YouTube. They captured the traces, then they divided the trace in 100 millisecond windows, and for each windows they measured network metrics. So like this, they obtained the dataset that we are going to use, and we will actually train a model to infer the quality of the chunks downloaded by users. So let's see directly what we need to run this code. So first, you will need to import some libraries, Python libraries. And of course, the libraries you need depend on the kind of algorithms you want to run. So for the moment, just simple, basic libraries will suffice for today. Okay, we already downloaded the dataset, and we can load the dataset into a data frame like this. Now the dataset is contained into the data frame df, and we can visualize the first 10 samples, or 11 samples actually. Okay, we can see already what are the columns, or the features, packet sent, packet byte sent, etc. If you want to know the data types of the different features, you can use df.info. For example, bytes received is an integer, IP src0 is an object, etc. So it is important to understand the meaning of the features. And to do so, we go back to the page of that describes the dataset, and we can check the description. So, okay, we have some specification of the event. That means whether the video client is experiencing a buffering phase, meaning that
the video is interrupted and the client is waiting for the chunks to be downloaded. Then some timestamp that we will not need. Then the playback progress. So this is the number of seconds that the user has already seen, has already watched. This is the total video length. This is the quality of the video chunks that are received. It goes from 144p up to HD 2160. Then you have buffer progress. That is the seconds of videos that is already into the client buffer. So you know that when you watch a video on YouTube or any other video streaming platform, you have a client running mainly in your browser, and this client is continuously downloading chunks, segments of videos. While it is downloading chunks, you are already watching chunks. So it is very important that you download more chunks than the ones that you've already seen. Like this, the player is always ready to reproduce the following chunk without waiting to download. So two processes are happening at the same moment: chunk downloading and video reproduction. And so buffer progress indicates how many seconds of videos are inside the buffer. Buffer health is how many seconds of videos are in the buffer that you've not already seen. So if you're at 1 minute 2 seconds and your buffer is filled with videos up to 1 minute 4 seconds, then you have 2 seconds buffer. Of course, the more the buffer health, the better, because it means that you will always have chunks to reproduce and you will not experience rebuffering. Okay, these are the main fields. It is important to also understand what are the values that the different columns can take. For example, with this command, we are checking, maybe I increase the zoom. So with these commands, we are checking what are the values that the column label can assume. And these are no quality, 480p, 360p, etc. These are the values that another column called buffer valid can assume, etc., etc. Then you can have a look at some simple statistics for each column by running this describe command. This will show you how many samples you have in each feature, then what is the mean of the feature across the entire dataset, the standard deviation, the minimum, and the percentiles, and the maximum. We will see what these things are later. But you can see that not all the columns are shown, because there are a lot of columns. How many columns? You can check by running these commands. So we have 200 columns. So with the command describe, you will not see them all. If you want to see them all, you have to use this command here that you can copy and paste from my notebook. Okay, just the same information, but with all the features, not just some of them. So let's start to define some first and second order statistics. Okay, so let's focus on feature J. Suppose it is packet sent or whatever. So the mean is, of course, the sum of all the all the values of that feature for all the samples divided by the number of samples. The variance gives you an idea of how much this feature varies from a sample to another, and it is given by this formula. So you take the average. Actually, this could just be, let me correct it. Sorry. Okay, so you take the mean of your data of your feature, and for each sample you compute the difference between the feature of that sample and the mean feature, and you do the square. and you do the average of these quantities. This gives you the variance of that feature. You may ask yourself why here we have 1 over m minus 1 and not 1 over m. Well, this is to have an unbiased estimate of variance. So you can see more information in this link I provided, but it's outside of the scope of this course. So you just have to remember that this is the correct formula of the variance. The standard deviation is just the square root of the variance. So sometimes it is easier to work with standard deviation because it is in the same scale of the actual features, while the variance is in the same scale squared. So sometimes it's completely ununderstandable what the variance is. So standard deviation is better. The box plot is the first nice visualization tool we will explore. Here we are showing the box plot of the feature called packet send. You see that it is composed by several lines. The central one is the median, which means that 50% of samples fall below this value here. Then you have the 25th percentile. That means that 25% of values fall below this value that I am indicating. The 75th percentile, and then the lower and upper whisker that we will see. Here I added some code just to let you understand how to compute these percentiles, 25th, 50th, 75th. But of course you will directly take these values from some Python functions that give you already the values for the percentiles. But just to understand, to compute, let's say, the 25th percentile, you just need to sort the values of your feature. So you take all the values, you sort them from the smallest to the largest, and then you visit 25% of elements of values, and you stop there. The value that you find there is the 25th percentile. In this case, for example, it is 7. This means again that 25% of your samples have that feature below 7. Then you have these lower and upper whiskers. What do they are? So to compute them, you need to first compute the interquartile range, which is the difference between the 75th percentile and the 25th percentile. So actually, if you see my mouse moving, what I'm indicating is the interquartile range. Then, to plot the upper whisker, you just start from the 25th percentile and you add 1.5 times the interquartile. So you start from the 75th percentile and you add the interquartile range multiplied by 1.5. You do similarly for the lower whisker. Of course, you have to take care of some very obvious things, meaning that the upper whisker cannot go beyond the maximum value. So if this is the maximum value, your upper whisker cannot go above it. So this minimum function here is there just to ensure that you don't go beyond the maximum value. And you do similarly for the lower whisker. Everything that is outside the interval between the lower and the upper whisker is considered an outlier value. Okay, here I'm showing you that you can plot in the same figure the box plot of different features. We can also group together samples in order to get more meaningful insights. For example, in this box plot, I'm grouping by label, meaning that, for example, if you look at the plot on the right, this box plot I am pointing at is just considering the samples whose label is 240p. So I'm just plotting the box plot of those samples. So I can do the same for the different labels, which gives me an idea of what is a sort of relation between the bytes received and the label. Because you can observe that when, as expected, when the quality is low, the resolution is low, the distribution of values of bytes received is lower than when the resolution is higher. So you see that the median here for 144p is way less than the median of 720p. So these can already give you useful information to understand relation between your target label and the actual features you have. Another important statistical tool is the histogram. So what is a histogram? A histogram is we can say is an approximation of the probability density function. So first of all, I will define it better, but first of all, if we try to just plot the histogram of the entire dataset with 200 columns, this is the result we have. Okay, there's too much information, we cannot see anything. So we need to select some columns that we think more meaningful and just to plot the histogram of those features. So this is the histogram of bytes received, of bytes sent, etc. As you can see, we divide the entire range of the value of bytes received into bins of equal size. And the first bins, for example, goes from, I'll put more zoom, maybe. It goes from, let's say, 0 to 500,000. And the height of the bar counts how many samples have bytes received between 0 and 500,000. The second bin is counting, the second bar is counting how many samples are within the range between 500,000 bytes received and 100,000 bytes received, etc. And we are doing the same with all the other columns. So box plots are interesting. Okay, before that, I would like to show you that the size of the bin is very, it changes all the visualization. For example, here in this figure, we let Python choose the number of bins we want to use. While in this other picture, we fixed the number of bins to 3. As you can see, the approximation of the probability density function is less precise, let's say, because we have larger bins. One bin goes from 0 to 150,000 bytes received, more or less, and then from that value to 300,000 bytes received, etc. So we may say, okay, so it may be better to increase the number of bins as much as we can. But if we do it too much, every bin is so small that we risk to have one sample per bin. So what we would have is a set of bars that is always counting 1. So finding the right number of bins is needs experimentation from your part. So you need to plot with different measures of bins and see what is the box plot that is more interesting for you. Histograms become very insightful when you combine them with the group by function here. For example, here we are just concentrating on bytes received, and we are plotting the histogram of bytes received of all the samples in this case, whose quality is 1080p. This is the histogram of bytes received of a sample whose quality is 144p, etc. So we can already see the differences between in the distribution of bytes of the feature bytes received with respect to the quality. So this we can already construct a very rudimental, let's say, inference algorithm that says that whenever we have a sample whose a connection whose bytes received is above this threshold here, 300,000, we are sure that the user is watching a video at 720p. Because if you look at the other quality levels, there are no samples whose bytes received are larger than 300,000. Okay? So if you're smart enough, you can already construct an inference algorithm just based on your observation on the histograms. Finding correlations between features is the most important part of data exploration because it tells you what is the dependency between a feature and the others. So we've already seen a way of looking at correlations, that is plotting the histogram of a certain feature, that is bytes received in this case, with respect to the when we change the label. Okay, and we see already that tendentially the quality, the largest the values of bytes received. Maybe the most direct way of finding correlations is to directly plot the entire dataset, one feature against all the other features, with the scatter matrix. First of all, so a scatter matrix is something that looks like that. Okay, we have one row per each feature and also one column per each feature. In each cell, we plot the entire dataset, and each point represents one sample. The x value of the point is the feature, in this case it's packets received of that sample, of that connection, and the y-axis value is the value of that sample in the feature packet sent. So first of all, notice that I'm here plotting not all the features but just a subset, because if I plot all the feature with just this command scatter matrix, I will have something that is not visible because we have 200 columns, and also it will take too much time to produce this image. So it's better to focus our attention on a subset of features, the ones that we think are the most important, and this is up to our intuition. So we can do scatter matrix of just the columns we are interested in. Note that this plot is ugly because there is overlap between the various name of features. So we have to restyle it a bit. In order to do so, I created a library, let's say, called visualization, in which I wrote different functions for visualizing purposes. So you are free to download it and to reuse it. So there you can copy and paste the address of this library. Here you can see the content that is in my GitHub as well. But you can directly download it with wget in your virtual machine on Google and import this library like this. And you can see what's inside. I wrote some small documentation with all the functions that you can find, etc. We will just use this one, if I find it, rotate label, okay? That will just rotate the name of the features of the scatter matrix. So if we run this, so we create the scatter matrix and we immediately say rotate labels with my function, we have something that looks a bit better. So let's check some interesting correlations. First, packet sent is positively correlated with packets received, as expected. So because the more chunks we want to receive, the more packets we have to send to request these chunks. Another interesting and obvious correlation, positive as well, is between packet sent and byte sent. We are talking about this cell. So the more packets we send, the more bytes we are sending. So and you can find yourself other interesting correlations. So these may appear like obvious, but as a sanity check, it's better you try to think of which kind of correlations you are expecting from your dataset, and you check if they actually verify as well. If they don't verify, you may have some problems in importing data. Maybe the name of the columns is not well positioned, etc. So these obvious checks are important to make. One other interesting correlation is between buffer health and buffer progress. Okay, this one. Because the more the buffer progress, meaning the more seconds you have in your video player already downloaded, the more the buffer health. So the more seconds you have ready to be consumed by your player. So the less probability you have of rebuffering events where your video is stuck and you cannot watch it for some seconds. Okay, here I wrote some other correlations that emerge from these scatter metrics, and you can do it yourself. Then observe that in the scatter metrics we don't have any indication of the quality, because the quality of the video chunk is a string in this moment, is not a number, and of course we cannot plot in a scatter metrics textual information. So what we need to do is just to translate these strings into the corresponding numbers. And this is what we are doing here. First, I wrote a function that replaces each string with the corresponding number. And then I apply this function to every element of the column label. And I add a new column to our dataset that I called label num, numeric. That is the result of this substitution, string versus number. This is actually okay. Now I want to visualize in my scatter metrics not only the previous features but also this new one that I just created. So columns to plot, I add to this vector, also to this array, also this the name of this new feature, label num. And let's run it. It takes some time, but then at the end we have our label num in our scatter matrix. One thing I forgot to tell you is that you can observe that in the diagonal you have the histogram of the various features. Okay, observe that among the label numbers we have also 0, which is the number we associated whenever the textual value of the quality was not among the values we know. So actually when the label number is 0, it doesn't mean that the resolution is 0. It means that we are not able to recognize the resolution of that feature. So actually this is equivalent to having not a number. Okay, so it may be misleading if we just keep these samples in our datasets, and to think that the samples with a 0 label num are the samples with the worst resolution. This would be misleading. So the best thing we can do is to just remove here. Okay, remove from our dataset all the samples whose label num is 0. So here what I'm doing is that I'm just taking the samples whose label num is different than 0, and I'm copying the result of this operation to this data frame cleaned, and I'm plotting again the scatter matrix of this clean dataset. And I should. Okay, now we have the scatter matrix of our cleaned data frame.
We can also summarize the correlation between features by using a single numerical value, which is the Pearson's correlation coefficient or the covariance, either one or the other. So let's understand how to compute them. So here, mu j is the average of feature j across all samples, and mu j prime is the average of feature j prime. Say that feature j is packets sent and feature j prime is bytes received or whatever. Xij is the value of sample I in the feature j. So we can compute this quantity for all the samples and then sum overall the samples of the dataset and divide by n-1. What we will have is the covariance between feature j and j prime. What is the meaning of covariance? You can observe that covariance is positive whenever when one feature j increases, the other j prime tends to increase as well, while the covariance is negative if it's the other way around. So whenever one feature increases, the other decreases. As an example, we have observed that whenever bytes sent increases, also packets sent increases. So we can say that we can expect that the covariance between these two features is positive. If we normalize the covariance with the value of the standard deviation of feature j and of feature j prime, like this, we obtain the Pearson's correlation coefficient, which has the same meaning, but it is ensured to be between -1 and 1. So Pearson's correlation coefficient of 1 means that actually the two features are the same, because they vary with respect to the average and in the same way. While if the Pearson's correlation is 0, it means that there is no relation at all between the two features. In this notebook, I showed you the code how to compute the correlation matrix, which is a matrix with the Pearson's correlation coefficient for all the features. So this is the correlation coefficient between packets sent and relative time, for example, etc. You can check the notebook yourself and observe what are the interesting correlations that the Pearson's coefficient tells you. So instead of looking at matrices with numbers, it can be nicer to look at a sort of heat map of the correlation between features. And I wrote a function for you that you can just utilize that is called plotcore inside the library visualization. And here is the result when I try to print the values of correlation in addition to the colors, and of course is a mess. Here is a better result when I try to just print the colors without any numbers, and it is more visible. Here we have all the features in the y-axis and in the x-axis. Of course, all the numerical features, not the textual features. And you have a color scale which goes from intense blue, -1, so when features are negatively correlated, like these couple of features that I'm pointing at, to 1 with intense red, meaning that the two features are perfectly correlated, like bytes received 1 versus packets received 1. In the next figure, I just plot the correlation matrix between a subset of features. So instead of having all of them, I have just a subset to make things clear. So you can play yourself with your code in your project. So now the final goal of the work that we are using, the dataset that we are using, is to infer the video quality based on network information. And the video quality, we said that is contained in this column called label num. So it is interesting to see what are the most correlated features to this label. And to do so, I wrote again a function for you that you can just utilize that is in this library called feature engineering that you can get from my GitHub in this way using wget, and you can just use it. Okay, the result is this. Of course, label num is perfectly correlated with itself, and then is negatively correlated with start time, epoch time, packets, and positively correlated with packet sent 0, etc. So observe that here I'm writing in this features core array that you obtain from my function. You have the features ordered by the absolute value of the Pearson's correlation coefficient with the target feature, that is label num. Okay, of course, in this dataset we observed that start time is very negatively correlated with label num, but this is just this is not really an interesting insight, because this depends on just the way these researchers perform the experiment. So evidently they just run first the experiments with higher resolution videos. But so the start time is actually the actual time at which the experiments took place. So it makes no sense to construct our model based on this feature, because in the reality we will experience other times, other timestamps. So the message here is that even if you have strong correlated features, it doesn't mean you have to use those features when you will build your model, because sometimes it's just a way in which the dataset is constructed that gives you this high correlation. Another thing you should take into account is that if, for example, we have two features that vary like this, x and y, of course you see that there is a strong relation between the two. It's a quadratic relation. But if you compute the Pearson's correlation, you would obtain 0. What does it mean? It means that Pearson's correlation is only able to capture monotonic relation between features. If the relation is more complex but is still there, Pearson's correlation will not be able to capture it. So don't just look at Pearson's correlation to understand if there is a relation between your features. Pearson's correlation is just one information, of course useful, but it's not all you might need. It may be very important for you in your project to transform the datasets to make it more easily understandable by a machine learning model. For instance, let's observe just these two columns from our dataset, kilobytes received and label num, that is our target. This is what we would like to infer when we construct the model. Observe that kilobytes received is very skewed, meaning that all the values are, most of the values are very, very small values. So it is like the distribution of values of kilobytes received is squashed toward very small values. This can happen a lot. And you see so that these samples here are not very well distinguishable. So your eyes cannot distinguish very well this point, and also machine learning models will have hard time to really distinguish these points. But we see intuitively that there is more information in within the low values of kilobytes received. So we would like to have some tools that allows us to make some sort of zoom in the low values of this feature. To do so, we can just transform this feature by replacing kilobytes received with the logarithm of kilobytes received. If we do so, we obtain something like this. First, we obtain that the values are now not skewed, but they are more normally distributed. The distribution is centered better, and also the points are more spread out. You will see that this is very advantageous when you want to construct machine learning models. We can already observe that this transformation allows us to unveil some correlation that was hidden before the transformation. In the code that follows, I just compute the correlation matrix again, this time using the
some features that have been transformed with the logarithmic transformation. And I do exactly the same operations as before, except that I use logarithmic features. And now if I print the most correlated features with the label num, you see that I have some values of correlation, Pearson's correlation coefficient, and you can see that they are overall higher than the values I had before the transformation. So observe that by having a smart transformation, I managed to increase the correlation between my features that I transformed and the target label that I want to infer. Logarithmic transformation is just one of them. There may be other transformations depending on your dataset, and I put here some other links for you to explore. With this line, I just save the dataset. I also invite you to go through another Python notebook in the same folder, Introduction, which is called B Preprocessing. In this notebook, I tell you how, two things actually, how to treat missing values and how to treat categorical values. Let's start with missing values. So many times in your dataset, there will be some samples which miss some feature value. So instead of the actual value, you will have not a number or a missing, or actually a missing cell. So what can you do in this case? I'll show you directly the code to do so. So, okay, the first operations are just the standard ones. I just download the dataset, etc. So, the first thing to check is whether there are columns which have missing values, and this is the code to do so. In this case, these columns are bytes sent and IP destination 0. It could also be useful to just represent the entire dataset, and with this code here, and when you see an empty point, this means that this sample, in correspondence to this feature, this value here is missing. For here, we notice, for example, that this feature here is missing a lot of values, while this other feature here is missing just maybe one value for one sample. Okay, so this is just to visualize whether there are missing values or not. What can we do with this? We have different strategies. First, if these missing values are not a lot, you can just remove the feature entirely from your dataset, so you ignore it, you don't use it to construct the machine learning model, or you can just remove the rows, the samples with the missing values. But the strategies, of course, work if you have enough samples or enough features, so that even if you remove some, you have still material to work with. Another strategy is inputting, meaning that you replace missing values with other values, which can be a constant, in this case 8, or which can be a number that is in some way similar to the rest of the dataset. So you use if a sample is missing a certain value for a certain feature, you use the other samples to construct a value that is credible, and you replace the missing value with this value. I let you explore the code in this Python notebook yourself, and if you have any doubts, don't hesitate to write. The second thing I want to show with this notebook is how to treat categorical features. So far we have just represented numerical features, but in our dataset, for instance, we have a lot of objects which are strings practically, which are not numbers. How do we deal with this? So let's take an example. One of the categorical features in our dataset is protocol 0. If we check what are the values it can take, they are 0, quick, TCP, TLS, UDP. So one fast solution could be to just associate quick with number 1, TCP with number 2, and so far and so forth. But this would be an error. Why? Because we would implicitly say that quick is less than TCP, and TCP is less than TLS. So we are imposing an order that doesn't make sense. So every machine learning model we will construct would exploit this order, but this order doesn't make sense. So we would end up with a erroneous model. What we should do instead, in these cases where categorical values do not have any ordering, is to use one-hot encoding. What does it mean? Let's see directly the code to achieve this. So here we are replacing protocol 0 with a set of columns, one column per each value that protocol 0 can take. And we put a 1 only in the corresponding value. So, for instance, the first sample here, the first row, was a sample whose protocol 0 was quick. And so we will put a 1 in protocol 0 quick and a 0 elsewhere. And we do the same with the second, with the third sample, etc. And these are just 2 lines to do so. You can just copy and paste this code. Again, I recall you to recap the definitions that we have given regarding all these statistical quantities, because they can be asked in the exam. That's all for the lesson. So let's see what we have seen today. So I have given some definition of AI and machine learning, some examples of application to communication network. We have seen what are the different machine learning methods, which means supervised, unsupervised, semi-supervised, etc. We have learned how to run code in Google Colab and how to perform some simple data exploration and visualization, the meaning and the computation of simple basic statistics. And we have done some pre-processing on our datasets. We have applied the logarithmic transformation to uncover the hidden dependence between features. We have learned how to deal with missing values and with categorical features by using one-hot encoding. In the next lesson, we will directly jump to supervised learning. So we will learn how to build our first machine learning model, in particular a linear and then a polynomial regressor. Thank you.